Hey guys, so today we're going to talk about chapter 14, section 2, which is solving trigonometric equations using inverses. And we have talked about inverses before, but now we're going to talk about it in terms of trig. So our objectives for this section are to evaluate inverse trig functions and to solve trigonometric equations. So we have seen inverses before, and they're very useful when we're solving equations. To solve x cubed equals 5, for example, we take the cube root of both sides to get x equals the cube root of 5. On the other hand, if we're solving x squared equals 5, we're going to take the square root of both sides of our equation, and our solutions are going to be the positive square root of 5 and negative square root of 5. Note, though, on your calculator, if you were to plug this in, it would only show the positive solution, but we have to remember for x squared, it's a plus or minus solution, so we have two solutions. Because trig functions are periodic, and remember periodic means that your y values are going to keep repeating based on a pattern, a trig equation like sine of theta equals 0 has infinitely many solutions. So if we graph the sine function, there are infinitely many places where it is equal to 0, and we can figure that out by starting with whatever 0 1 0 and then adding to figure out a coterminal angle. So in this case we would be adding pi over 2 for this function. Any inverse function for sine of theta must, however, give only one solution. So if we talk about the inverse of sine theta, for that function to be 1 to 1, we can only have one input. So I'm not going to be too strict about this. I'm just going to talk about it a little bit, specifically regarding your calculator. So when we're talking about cosine of theta, this chart is saying that the range is from -1 to 1. That's because the amplitude is 1. Now the domains, notice the red parts in this chart are things that are different. The domain we know for cosine of theta is going to be all real numbers. However, if we're talking about the inverse function, for the inverse to be a function as well for cosine, we're going to say that the domain is between 0 and pi inclusive. So when you take the inverse function, when the domain and the range flip, your inverse will still be a function. For sine and tangent, however, your domain is going to be from negative pi over 2 to pi over 2. And one thing that you have to remember, for tangent, the range is going to be all real numbers, thinking back to that graph. So your range is all real numbers. And then when you take the inverse, your domain becomes all real numbers. So when you're talking about inverse functions, from the function to the inverse, your domain and your range flip. So your domain becomes the range for the inverse, and your range becomes the domain for the inverse. And in contrast to trig identities, some trig equations are true for only certain values of the variable. So sometimes we're going to want to check our answers. So let's look at our first example. What is inverse cosine of 1/2 in degrees? So note this -1 is not a power. So this isn't cosine raised to the negative first power. That is representing our inverse, just like we used to write our function as an inverse like this. So that's not to a power, that's just representing our inverse. And when we're talking about the inverse, we're trying to solve for the angle. Oops, sorry, I erased my 1/2. We're trying to solve for the angle, so we're solving for theta when cosine is equal to -1/2. So we're given our answer and we're trying to look for the angle that gives a cosine value of +1/2. So let's think about our graph here, coordinates. So in cosine, we know that our domain is going to be from 0 to pi, and that's because in the first quadrant, cosine is positive, and second, cosine is negative. If we keep going through this coordinate plane, we get back to negative and positive, so then everything just starts repeating. So we don't have to worry about quadrants 3 and 4 for cosine. We have a positive quadrant in 1 and a negative quadrant in 2, so we'll be able to determine our answer. So when cosine is equal to +1/2, so obviously our angle or our answer is positive, that means we're going to be in the first quadrant. So we have 1/2. And remember, 1/2, cosine represents our x values, so our x coordinate has to be 1/2. That means our y coordinate is going to be radical 3 over 2. That's the ordered pair that we know of in our unit circle, which means that this is going to be a 60-degree reference angle. We know that based off of this point. If cosine is equal to 1/2, that means our x value in the point is 1/2, which means the y value is radical 3 over 2. So this is a 60-degree angle. So in this case, our theta is going to be 60 degrees. Looking at another example, we have what is the inverse sine of negative radical 3 over 2 in radians. So notice now this time we're talking about radians. Or we're looking for our angle in radians. So we're still looking for our theta when sine is negative radical 3 over 2. So thinking about our coordinates, for sine, our domain is from negative pi over 2 to pi over 2. So we're only talking about quadrants 1 and 4 in this case. In quadrant 1, sine is positive. In quadrant 4, sine is negative. So we have all the positive and negative y values that we need to figure out our theta. So if sine is negative 3 over 2, that means we're going to be in quadrant 4 for a negative value. Sine represents the y values of our ordered pair, so that means our coordinate is going to be 1/2 comma negative radical 3 over 2. And this represents a 60-degree reference angle. So this reference angle is 60 degrees, but we're asked what our theta is in radians. So we have to figure out this in radians. 60 degrees in radians is pi over 3. But now be careful, because we're only talking about quadrants 1 and 4. So to get to pi over 3, we're going to have to move from our initial side, we're going to have to move in a clockwise direction, which would make this negative pi over 3. So in this case, our theta is going to be negative pi over 3. And if you plug this value into your calculator, you'll get the same thing. This is just based on our domain, which is from negative pi over 2 to pi over 2. Okay, so let's look at another example. What is the inverse cosine? Negative 1/2 in degrees. So again, we're looking for the angle or the theta that is going to give us cosine of 1/2. And now we're talking about degrees. So if we draw our coordinates, again, cosine is from 0 to pi for our domain, but in this case, we're talking about degrees, so I'm going to make this 180 degrees. So in our first quadrant, we know cosine is positive. Second quadrant, cosine is negative, and we're trying to find a cosine value of when it's negative 1/2. Sorry, this should be negative 1/2. That means we are in our second quadrant. When cosine is 1/2, that is a 60-degree triangle. So to figure out our theta, because we're only talking about the first and the second quadrants, we have to go from our initial side. If our reference angle from the negative x-axis to our 1/2 is 60, that means from the initial side all the way around here, our theta is going to be 120 degrees. So theta in this case is 120 degrees. That is the angle that is going to give us a value of negative 1/2. And one more example for this. What is inverse tangent of negative 1 in radians? So again, we have the answer, we're looking for the angle. So theta equals inverse tan negative 1. And for tangent, we're talking about the same restrictions as sine. So we have negative pi over 2, pi over 2, and 0, because tangent is y over x. So that's going to give us the same restrictions as our sine. So we're talking about a tangent of negative 1, which means we're going to be in the fourth quadrant. Negative 1 means that we have the same exact numbers. We're dividing by the same thing, top and bottom. So this is going to be a 45-degree reference angle, which makes in radians, our theta negative pi over 4. So theta is going to equal negative pi over 4. Again, if you plug this value into your calculator, you will get theta of negative pi over 4. There are multiple answers, but for this inverse to be a function, for it to be 1-to-1, based on the restrictions, your calculator is going to figure out the theta, which is going to be negative pi over 4. And again, so now we're going to solve trig equations. And just to reiterate, in contrast to trig identities, most trig equations are true for only certain values of the variable, which is dependent on our restrictions based on the domain and the range. So let's look at an example for solving trig equations. So what values of theta, and notice I'm telling you that theta is going to be between 0, including 0, and 2 pi, satisfy the equation. So our equation, we have 3 cosine theta minus 1 equals cosine theta. So just like when we're trying to solve other equations, say we rewrite this as, instead of cosine, instead of in terms of trig, we're going to write it with a variable. So say we say 3x minus 1 equals x. I know we all know how to solve this. To solve for x, we need to isolate our variable. We're going to subtract x from both sides, and we would be left with 2x minus 1 equals 0. Then to get x by itself, we would add 1 to both sides, so 2x equals 1. Last step to solve for x would be divide both sides by 2, and x would be equal to 1/2. When we're solving with a trig function, it is the same concept. So keep the way we solve equations normally, keep that in mind. We're going to be doing the same thing. Now we just might have a trig function. So looking at this equation, we need to solve, we're trying to isolate our variable, which in this case is theta. We're trying to find the values of theta. So we're going to do the same thing. We're going to subtract cosine of theta from both sides to get our variable to the same side of the equation. Now these are like terms, so we can subtract. So we have 2 cosine of theta minus 1 equals 0. Next step, we're going to add 1 to both sides. And we're left with 2 cosine of theta equals 1. Divide both sides by 2, and we have cosine of theta equals 1/2. Last step, we need to isolate theta. So when we isolate theta, to move that cosine to the other side, that's going to become the inverse. So theta is going to equal inverse cosine 1/2. So now we have an equation that we're familiar with. We just worked with these types of problems. So theta is going to equal inverse cosine 1/2. So we're looking for our angle, we're looking for the theta when cosine is equal to 1/2. So we're going to go back to our coordinate plane. So cosine is positive, our answer is positive, and we know that cosine is positive in quadrant 1 and in quadrant 4. Remember that acronym I talked about earlier? All students take calculus. So all represents all trig functions are positive. In the second quadrant, only sine is positive. Third quadrant, only tangent is positive. And fourth quadrant, only cosine is positive. So right now, we're talking about cosine, so we're only worried about the first and the fourth quadrants. Now we have cosine is 1/2. So we know if cosine is represented by our x value. So when it's 1/2, that means we have a 60-degree triangle, or pi over 3. So in our first quadrant, this value is going to be pi over 3. In our fourth quadrant, this value is going to be negative pi over 3. So we can think quadrant 1, we're going to have pi over 3. Quadrant 4, we're going to have negative pi over 3, but we don't want to leave our answer in negative, so to figure out a positive value, we're going to figure out a coterminal angle. So if you forget how to figure out coterminal angle, in this case, because we're in radians, we're going to add 2 pi, but to keep a common denominator, we're going to add 6 pi over 3. So in quadrant 4, our value is going to be 5 pi over 3. So to write our solution, we want to keep our equation. We're going to write our equation first. So theta equals inverse cosine of 1/2. And in this case, for theta, we can have a theta of pi over 3, or we can have a theta of 5 pi over 3. And the reason we have two solutions now for this equation is because our restrictions change. Now we're thinking about from 0 to 2 pi. So our restrictions change, which could leave us with more than one solution. Looking at our second example, we have what are the values of theta between 0 and 2 pi that satisfy the equation. We have 3 sine squared theta plus 4 equals 2 sine squared theta plus 5. So notice now we have our trig functions are squared, so we're just going to think about this as a quadratic equation. We're going to do the same exact thing in order to solve for theta. So we need to move our functions to the same side. So I'm going to subtract 2 sine squared theta from both sides. So these cancel out. While I'm doing that, I'm also going to subtract 4 to move our numbers to the other side. Now notice these are still like terms, so we're left with sine squared of theta equals 1. So we're almost done it. And remember, when we're writing, if we have a trig function that is squared, remember your squared has to go between the function and the angle in order to not need parentheses. So it has to be written like this. Now to solve to get rid of that squared, we're going to take the square root of both sides, and we're left with sine of theta is equal to positive or negative 1. Very important. Don't forget that plus or minus. You need that because that's going to give us more than one solution. You can't forget when we're squaring, we can plug in a positive or a negative value. So don't forget about that. So our equation for theta, we can solve inverse sine of positive 1. Sorry, that doesn't look much like a inverse of positive 1 or inverse sine of negative 1. So we're looking for our angle when sine is positive 1, and we're looking for our angle when sine is negative 1. So looking at our coordinate plane, remember for sine we're going from, in this case our restrictions actually, are between 0 and pi over 2. So when sine is 1, when our y value is positive 1, we're at pi over 2. So theta is going to equal pi over 2. Because our coordinate up here is 0, 1, sine represents the y value. When sine is negative 1, we are on the negative x-axis, and that's 3 pi over 2. Because our coordinate here is 0, negative 1. So theta can also equal 3 pi over 2. So the values of theta that satisfy this equation are pi over 2 and 3 pi over 2. And to check, you can always plug these values back into your equation and make sure everything works out. Okay, so for this next problem, we have find the complete solution in radians of the equation 2 sine squared theta plus cosine theta minus 1 equals 0. And there are a few things that we have to notice before we start this problem. First, we're told to find the complete solution. So that means we have to interpret all the values. We're given no restrictions, and there are going to be infinitely many solutions. The other thing we have to notice, we have 2 sine squared theta plus cosine theta minus 1 equals 0. So we have two different trig functions, and we don't want that. That's like having two different variables. So we need to convert one of these functions in order to make this an equation with only one function. So cosine theta we can't really convert, but if we think about sine squared theta, we can convert that because we know from our Pythagorean identities that sine squared theta is equal to 1 minus cosine squared theta. So all we're going to do to convert, we're going to plug in we're going to substitute 1 minus cosine squared theta for sine squared theta. And when we do that, we're left with 2 times 1 minus cosine squared theta plus cosine theta minus 1 equals, not cosine squared, sorry. Just cosine theta. Minus 1 equals 0. So now we're just going to think about this like a quadratic function. To solve, we're going to distribute this 2 to both of our terms. So we have 2 minus 2 cosine squared theta plus cosine theta minus 1 equals 0. Next thing we're going to do is combine our like terms. And we're left with negative 2 cosine squared theta plus cosine theta plus 1 equals 0. So now there's a regular quadratic function, but to make our lives a little bit easier before we start to try and factor, we're going to divide everything by negative 1. Because our first term is negative, it's much easier to factor when you have a positive first term. So we're just going to divide everything by 1. That's going to flip our terms and make the first term positive. So that gives us 2 cosine squared of theta minus cosine theta minus 1 equals 0. So now from here, if you're given an equation like this, you should be able to factor. So now we're going to factor. When we factor this function, we get 2 cosine theta plus 1 times cosine theta minus 1. You can always equal 0. And you can always double check by foiling and making sure you get back to this step previously. So we factor, we have 2 cosine theta plus 1 times cosine theta minus 1 equals 0. So now, remember back to when we were originally factoring, solving equations, we have to set each of these expressions equal to 0. So we have 2 cosine theta plus 1 equals 0, and cosine theta minus 1 equals 0. I'm just going to move this on to the next page so that we have a little bit more space to work. So after we factor and set both sides equal to 0, we are left with 2 cosine theta plus 1 equals 0, and cosine theta minus 1 equals 0. Now we still have to solve, so we're solving each side for theta. So on our left side, we're going to subtract 1 from both sides, and we're left with 2 cosine theta equals negative 1. Divide both sides by 2, and we have cosine theta equals negative 1/2. In order to solve, we're trying to isolate theta, so we get theta equals inverse cosine of negative 1/2. So that's our equation. We need to keep this equation. That's what we're trying to solve for theta. And on our right side, we're just going to add 1. So we have cosine theta equals positive 1. To get theta by itself, we take the inverse cosine of positive 1. So these are our two equations. They're very important in order to solve. So the next thing we have to think about is where we are on our unit circle. For our right equation, we have theta equals inverse cosine of positive 1. And remember, we're looking for all, find the complete solution. So we're looking for all solutions. We have no restrictions. So when cosine is positive 1, that's at this point here, where our point is 1, 0, and that is 0 on our unit circle. So in that case, our theta is going to be equal to 0. But we have to think about all of our solutions. So to figure out the rest of our solutions, we are going to add 2 pi. We're going to figure out coterminal angles. But rather than if we add 2 pi, we get 2 pi and then 4 pi and then 6 pi and so on, rather than writing out infinitely many solutions, we're going to shorten that by adding 2 pi n. And in this case, n represents the number of rotations from that point. So the first time we go around, it's going to be 2 pi. The second time is going to be 4 pi, and so on. And we have to do that in the negative direction as well. So for your complete solution for inverse cosine is 1, theta is going to be equal to 0 plus 2 pi n. That's going to give us the complete solutions for every theta. Now, if we think about cosine theta is equal to inverse cosine of negative 1/2. We've talked about this one a little bit before, but let's look at our coordinate plane. Now we have a negative cosine, and because we have no restrictions, we're looking at all 4 quadrants. Cosine is negative in the second and the third quadrants. So in the second quadrant, when it's negative 1/2, remember that's going to be a 60-degree angle. 60-degree reference angle, or our in radians it is pi over 3. But in the second quadrant, that's going to be 2 pi over 3. And in the third quadrant, that is going to be 4 pi over 3. So in this case, for theta, we're going to have 2 solutions because we're in 2 different quadrants. Theta is going to be equal to 2 pi over 3. That's our one solution. To find the complete solutions, we have to add 2 pi n. Or theta is going to be equal to 4 pi over 3 plus 2 pi n. So from that original equation where we had cosine theta equals negative 1/2, we get our equation to solve for theta, and then we could figure out our solutions, which are going to be 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 2 pi n. And in both of these equations, it's important to write the step before when we've isolated theta. We're going to need that equation. So make sure you have that written out. So anytime you're solving, you're asked to find complete solutions, you have to add the period, which in this case for cosine is 2 pi. You have to add the period times n, and again, n is the number of rotations. Okay, so let's look at another example. And I know these are tricky, that's why we're going to go over a bunch of examples so you can have a lot of practice, and watching me do these will help. So find the complete solution in radians of the equation. So again, we're finding the complete solution, which means we have no restrictions, so we're going to have infinitely many solutions. So we have 2 sine theta plus 1 equals cosecant of theta. And now remember, we have 2 different trig functions. It's like similar to having 2 different variables. We want to get our equation in terms of one function so that we're able to solve. So I know that cosecant of theta is equal to 1 over sine of theta. So that will give me my equation in terms of sine. So I'm just going to replace cosecant of theta with 1 over sine theta. And that gives me 2 sine theta plus 1 equals 1 over sine theta. Now we have this equation. On the right side, we have a fraction, but we can get rid of that fraction just by multiplying. So I'm going to multiply both sides of my equation by sine theta. When we multiply both sides by sine theta, our right side, these are going to cancel out, and we're left with 1. On our left side, I'm going to distribute this sine theta to both terms, and we're going to get 2 sine squared theta plus sine of theta equals 1. And this is kind of similar to our last problem, where it's like a quadratic equation, so we're going to move our 1 to the other side by subtracting, and then we should be able to factor. So when we move 1, we have 2 sine squared theta plus sine theta minus 1 equals 0. And you'll notice this time our first term is positive, so we don't need to divide by anything in order to get a positive first term. Now we are able to factor. And we're factoring normally just like a quadratic equation. When we factor, we should get 2 sine theta and sine of theta. Because our middle term is positive, that's going to give us plus 1 in our second parentheses, minus 1 in our first set of parentheses. Now, after factoring, to solve, we're going to set each of these expressions equal to 0. So we have 2 sine theta minus 1 equals 0, and sine theta plus 1 equals 0. And I'm going to move on to the next page so that we have plenty of room. So now we are solving. And again, we have 2 sine theta minus 1 equals 0, and sine theta plus 1 equals 0. And we're going to try and solve for theta because we need an equation that's going to represent our angle. So in our equation to the left, we're going to add 1 to both sides. So we have 2 sine of theta equals positive 1. Divide both sides by 2, and we're left with sine theta equals 1/2. We're solving for our angle, or theta, so we need to get rid of that sign. So we're going to have theta equals inverse sine of positive 1/2. So that's our equation that represents the angle. For our equation on the right side, we're going to subtract 1, so we have sine theta equals negative 1. Take the inverse to get theta by itself, so we have inverse sine of negative 1. Now to solve for our theta, we're going to look at our coordinates. For sine, when sine is negative 1, just like that problem we talked about before, sine is negative 1 at 3 pi over 2, because that coordinate is 0, negative 1, and sine is represented by the y values. So sine is going to be negative 1 when theta is 3 pi over 2. So we can write our solution as theta equals 3 pi over 2, but remember we're looking for the complete solution, so we're going to have to add 2 pi and the number of rotations. So our solution for this is 3 pi over 2 plus 2 pi n. For our other equation, we're looking for our theta when sine is positive 1/2. So we have to think about when sine is positive. Sine is positive in the first and the second quadrants. So now let's think about our angles. If sine is 1/2, that means we're going to have a 30-degree reference angle, which means that we're at pi over 6 in the first quadrant and 5 pi over 6 in the second quadrant. So our theta in this case is going to be equal to pi over 6 plus 2 pi n, and theta equals 5 pi over 6 plus 2 pi n, and those are our complete solutions. Do not forget to add 2 pi n, because otherwise you're not going to have infinitely many solutions. Now the last type of problem that we're going to talk about in this section, we have solved the trigonometric function in terms of y. So now we have an equation in terms of y, and we're trying to solve for theta. Now notice this equation looks like what we did in chapter 13 with transformations, where there are going to be restrictions for these types of problems. So if we think about the graph of sine, we start at 0 and it looks not exactly like that. And it'll look something like this. Not to scale, it's not exact. And then from this equation, we know that our amplitude is 2, which means that every point is getting multiplied by 2. So it would look something like this. And then we have a vertical shift up 4 units. We're moving up 4 units. So we have to take those transformations into account, because that's going to change our restrictions for this problem. So our restrictions, we're going to think about our y values. So for this problem, our restrictions are going to be on the y values, and for y values we have to think about our amplitude, because our amplitude is what determines the range. So in this case our amplitude is 2, which means that without any other transformations our graph is going to have our minimum point at -2 and a maximum point at 2. But now we have a vertical shift up 4 units, so we have to add 4 to both of these terms to get a range of 2 and 6. So you're taking your amplitude and then you're adding the vertical shift, and that's going to give us our restrictions for y. So our range is going to be between 2 and 6, including these values. That's very important for this type of problem. You have to determine your restrictions. Now, going back to our equation, after we figure out our restrictions, we have to solve for theta. So we're trying to isolate theta. So we're going to think about this as a regular equation again. First step, we're going to subtract 4 from both sides, and we have y minus 4 equals 2 sine 3 theta. To get sine 3 theta by itself, we're going to divide both sides by 2, and we have y minus 4 over 2 equals sine of 3 times theta. Now this is where it gets a little bit tricky, because now we don't just have sine of theta, we have sine of 3 theta. But we're going to keep that 3 theta together for now. For the moment, we're keeping 3 theta together, and we're going to use the inverse again. So we have inverse sine of y minus 4 over 2. So that's very important. You're taking the inverse first, and you're leaving theta with whatever it's being multiplied by. Now, I didn't specify in the instructions, but we are looking for the complete solution. So again, we have to add 2 pi n to this equation in order to get all of our solutions, our infinitely many solutions. Now, from this point, to get theta by itself, we're going to divide both sides by 3. And when we divide both sides by 3, we are left with theta equals inverse sine of y minus 4 over 2 divided by 3. Running out of room a little bit down there. Let's see. I'm going to rewrite this so that you can see it. So we have theta equals inverse sine of y minus 4 over 2, all divided by 3, plus 2 pi over 3 n. And there is another way to write this. I'll show you that in the next problem. But this is your final equation solved for theta with your infinitely many solutions. And notice this term here, 2 pi over 3, that should always match up with your period, the period of your function, because for the period we're doing 2 pi over b. In this case our b value is 3, so that term, another way to double check is to make sure that term matches your period. And don't forget this n, it has to be multiplied so that we are finding our infinitely many solutions. Now the last problem for this section, we're going off the same idea. So we have solve the trigonometric function in terms of y, and we have y equals negative 3 cosine 6 theta minus 1. So if we think about our graph of cosine, we start at the amplitude and it looks a little bit like that. Now, we have to figure out our restrictions again. So our restrictions are going to be based off of our y value. So our restrictions for this function, again, you're starting with your amplitude. So our amplitude is negative 3, so we have negative 3 and 3, and then we're adding the vertical shift. So in this case, it's going to be minus 1 and minus 1. So that gives us a range of negative 4 and 2. So our y values have to be between negative 4 and positive 2. It's very important. You have to find your restrictions for these when you're writing these equations. So now we can look at our equation and start to solve for theta. So first thing we're going to do is add 1 to both sides, and we have y plus 1 equals negative 3 cosine of 6 theta. Next thing we're going to do to get cosine of 6 theta by itself is divide by negative 3. And when we divide both sides by negative 3, remember, we'd rather not have a negative in our denominator. So I'm just going to bring this negative outside and leave this as y plus 1 over 3, so our denominator is positive, equals cosine of 6 theta. Next, remember, we're multiplying our angle by 6, so we have to get rid of the cosine first. So when we solve for 6 theta, we're going to have inverse cosine of negative y plus 1 over 3. And to make sure that we're finding all the complete solutions, we're going to add 2 pi n to the end of this equation. Next step, to get theta by itself, we're going to divide both sides by 6. And our equation that we're left with is theta equals, now another way to write this rather than keeping our fractions, you can write this as 1 over 6 times inverse cosine of negative y plus 1 over 3. And notice this is going to simplify here when we divide by 6, plus pi over 3n. So we had 2 pi over 6, that's simplified to pi over 3n. This pi over 3 should match up with your period, which it does. And here we are finished. So our equation is going to be theta equals 1/6 inverse cosine negative y plus 1 over 3 plus pi over 3n, and that's going to give us our complete solution. So that's it for this section. If you have any questions, please feel free to email me whenever. I'm always ready and willing to help. Your homework is posted to Google Classroom. Good luck.